Greetings, everyone. Let's talk about solving exponential equations. That's going to be some sort of equation that involves a variable in an exponent. So for example, what power would convert 6 into 13, right? What power could I raise 6 to get a value of 13? And that's not a very nice number. It's going to be an irrational number, right? So we're going to talk about how to solve for things like that. What we're going to use is either one of two properties that we've already discussed in an earlier video on logarithmic properties. Remember, logarithms calculate exponents. So if I'm looking for an exponent, logarithms are going to be the perfect tool. Okay, so I could use the property where I act a log on an exponential and the bases are the same, so they basically undo each other, living behind just the power. Or I can use a property from the more advanced properties where if I have an exponent on the inside of a logarithm, I can just bring it out front as a multiplication. Okay, I'm only going to use that one if I happen to be using this particular other method where I only use the natural logarithm. Okay, so let's start with this property first. If I'm going to bring up a logarithm that happens to be the same base as an exponential I have already. Okay, so here I'm going to solve this one using this method right here. So let's separate this out. Okay. All right, so the first thing I'm going to do is I'm going to rewrite this. And what I want you to see is that I'm going to bring up a logarithm, because that's how I solve for exponents. To use this property, I just have to match the base. So I'll be bringing up a log base 6. But of course, normal, natural, golden rule, if I do something to one side, I have to do it to all sides equally. So if I bring up a log 6 on this side, I have to bring up a log base 6 on this side also. So if I use this property now, I have a logarithm and an exponential acting on each other with the same base. Therefore, they would undo one another, leaving behind just the x is equal to log base 6 of 13. Depending on where you need to go with this answer, you could stop here, or you may have to go a step or two further. Let's say I have to go all the way to the decimal, like if this is some application where I need to find it on a graph or in real life or something like that. This isn't going to be enough. This is an exact answer and x is isolated, but I don't have a log base 6 button in my calculator. So remember, I have to convert any other logarithm into some other base that the calculator already has, right? In this case, that's going to be me doing the change of base formula. ln of 13 divided by ln of 6, right? Because it would just be the argument over the base would be equal to x. Okay. Now those are two logarithms that I can punch up in my calculator now. So that would be ln 13 divided by ln 6. And I get 1.4315. Okay. All right. Now let's talk about the other method. The other method is not to go straight for what can I eliminate, what can I get rid of. I'm going to go straight for what would be easiest to write in the least amount of steps and get straight to something that I can punch into the calculator to get that numerical answer, right? So in this case, I'm going to use this property right here. If I happen to act a logarithm, any logarithm, on an exponential, I can simply pop the exponent out as a multiplication, right? And I'm going to use ln because that's the logarithm that we use a lot these days. It's a lot less writing for me, one less letter, right? So I'm a lazy mathematician like a lot of them out there. but it is the most straightforward one. So look, take the same equation, right? And instead of bringing up a log base 6 like I did last time, this time what I'm going to be doing is just bringing an ln in on both sides. A natural logarithm, remember that's base e, right? And of course, nothing's going to cancel or wipe out or get rid of each other here, but that's okay. I've got this property where I can bring the exponent out as a multiplication. So that would look like this. X times ln 6 equals ln of 13. And then to solve for x, you just have to notice that all this is a multiplication of some number, right? The logarithm actually doesn't have the variable in it now. Okay, so technically this isn't even a logarithm equation. This is actually a linear equation because I have x to the 1 times some number equals some other number. We already know how to solve that. X times a number, you divide the number to both sides, right? I'm going to divide both sides by ln 6. Notice that where that lands you is exactly where we were here. I then have x is equal to ln of 13 divided by ln of 6, which of course is the same approximate answer as the other one. Okay? This is the method that you'll find that I'll be employing most of the time, and that's so I don't have to do a lot of logarithm converting, and I'll have one base that I use all the time, and I'm used to hitting the button, and it becomes a regimen. It's just more efficient, okay? And then later on, in one of the later sections, we actually have a lot of applications that are base E. So in that case, the ln is a double whammy. Not only is it more efficient because you're using it a lot, but also the ln and the E would act well together. Okay. So right here, I want to solve this equation, right? It's the next step up from those. This equation just has a few more things in the exponent, but I'm still going to solve it the same way. I'm going to bring up a logarithm on both sides, right? So separate it out to make some space for my logarithm. I'm just going to use ln again, like so. All right. Just like before, I'm allowed to bring my exponent out. So I can bring the 3x minus 4 out. Okay. Now in some cases, when you have a number multiplied by a parentheses, they prefer you to distribute it. In this case, it's actually okay to just go ahead and get rid of the ln7 to the other side, right? In this case, since this is a multiplication and there's no x's in the ln7, I'm simply going to divide both sides by that ln7. So that what I end up with is 3x minus 4 is equal to the ln of 58 divided by the ln of 7. Okay? From here, it's completely linear. Well, of course, technically it was linear here too. From here, it's just get x by itself, right? I'm going to add the 4 to both sides. Notice the plus 4 is outside of the fraction, right? Because I just added it to both sides. And then I want to divide by 3. Now be careful here. I don't want to just make it a sloppy division of everything by 3. Instead, what I'm going to do is think of it like I'm multiplying by 1/3. So when I multiply by 1/3 here and here, it just makes my answer a little bit more efficient looking. Okay, so what I have is that x is equal to the ln of 58 over 3 ln of 7 plus 4 over 3. Right? And again, depending on your situation, that is a completely acceptable way to leave the answer. Or if you happen to need the decimal, of course you can plug this into your calculator. Okay? Be careful when you're plugging this in the calculator that this 3 times ln 7 is kept together. You're going to want to have a set of parentheses around that. And the calculator is going to want to put a set of parentheses around the 7 and the 58 just because the ln is an operator on the number. Okay? So let's see what we get here. I've got ln 58, close my parentheses, divided by, open a parentheses for the denominator, 3 ln 7, close the ln 7, close the denominator, so you have to do 2 parentheses, right? Then I'm going to do plus 4 over 3. So I get 2.02888. 49, so that's good. Okay. All right, next, find the x-intercept for this particular function. And notice it's an exponential function, right? We already know how to graph this from our earlier lecture a couple ago on exponential functions, right? This is an exponential function, 5 to the x. It has been reflected vertically. It's been shifted 3 to the right and shifted 2 up. So then we should have, something like this. Reflected makes it go downward, right? Then it's been shifted up and to the right. So I should have a horizontal asymptote at y equals 2. And then somewhere at 3, 1 should be my center here. So we're looking at something like that, right? We want to know where the x-intercept is. So we're looking for this location right here. And since I've already identified my center there as 3, 1, right? The center point there. I knew that because 3 minus 3 is the 0 here, so that's where my center x is, and you just plug it in. But we're looking for the x-intercept there, right? Okay. Definition of x-intercept: everywhere y is 0 on a function. So I need to solve the equation 0 equals 2 minus 5 to the x minus 3. Just need to solve that equation. Okay, well, I can take this, it's a negative right now. If I add the 5 to the x minus 3 to both sides, right? I'm basically just shifting it to the other side here. And plus 0, it stays the same. So I have 5 to the x minus 3 equals 2. Now it looks a lot like the equations we've been solving, right? I just need to figure out what that x is in the exponent now. So right here, to get at the exponent, I need to bring in a logarithm, right? If there's an exponent in question, going to need a logarithm. And I've been using ln the whole time. No reason to stop now. So I'm going to put an ln on both sides. ln of 5 to the x minus 3 is equal to ln of 2. I can bring the x minus 3 into the front as a multiplication. X minus 3 times ln 5 equals ln 2. Just like before, this is one of those situations where I can just go ahead and get the ln out of the way because there's no other x's on this side that I would have to interact with. So I'm going to divide both sides by the ln of 5. Okay, so I have x minus 3 is equal to ln 2 divided by ln 5. And then I'm just going to add the 3. So I have x equals ln 2 divided by ln 5 plus 3. And of course, since this is me finding an x-intercept, which could potentially help me make a more efficient graph, I really want the decimal, right? So let's punch that up. ln of 2 divided by ln of 5, right? And then plus 3. Wait, where's the plus 3? There it is. 3.431. Right? Just like we expected. Something slightly further along than 3. Right? Almost 3.5. Here's that graph in a much more accurate fashion. Notice the horizontal asymptote of the exponential function at y equals 2. Notice the center point of the function, just like we've graphed before, at 3, 1. And then the x-intercept, like we just calculated it, at 3.43. Let's step it up a notch. Let's do these last two examples of exponential equations here. Notice the major difference is that I have an exponential on both sides now, right? So that means there's variables to play with on both sides. So I'm actually still going to approach it the same way. It's just going to have a lot more steps. Remember, in your mind, don't tell yourself this is a more difficult problem. It isn't. It is more lengthy. It has more steps, but it's not more difficult. Okay? So here we go. I want to get at an exponent. So the first thing we need to do is throw in a logarithm, right? Okay. So I've got ln for 3x plus 6 and ln 11 to the 5 minus x. I have that property where I can bring exponents out of a logarithm. So the 3x plus 6 comes out times ln 4, and the 5 minus x comes out times the ln of 11. Okay? Now we're in an equation that's actually linear. Okay? And I know it looks complicated because it has the logarithms in it, but for just a moment, I want you to think and pretend that we're actually solving this equation right here. Just real quick. 3x plus 6 times 8 is equal to 5 minus x times 7, let's say. If you were given this equation, what would be the first thing you would do? Right? Well, wouldn't you want to get rid of the parentheses so that I could get my x's together, right? The whole idea is to get x's together on one side. So wouldn't you distribute first on both sides, right? And then take whatever you have, 24x in this case, and the minus 7x in this case, right? 35 plus 48, right? And then wouldn't I try to get my x's together? I want you to realize that this equation is no different. The structure is identical. Even though this is a logarithm, it's not a logarithm with a variable. This is a number. So I can simply treat it like a number. The first thing I'm going to do is I'm going to distribute that ln4 in. So what I have is 3x times the ln of 4 plus 6 times the ln of 4. And then the same thing on the other side. I'll have 5 ln of 11 minus x ln of 11. Okay? What would be the next thing you would do here, right? Wouldn't I add that 7x to both sides and try to get all my x's together? And then wouldn't I subtract the 48 here, right? So that I can work all that together? Yeah, that's absolutely what you would do, right? No different. what I'm going to do is I am going to add x ln of 11 to both sides. So that this one is gone. Now think about that for a second. What I actually did was I took something that had x in it and I just moved it to the other side so that my x's will be together. I can't actually add these, they're not like terms, but I can at least get them together on a side. Well, same idea, right? Neither of these have an x in them, so those should be the ones that I should be grouping away from x, right? So I'm going to subtract the 6 ln 4 in order to get rid of this one. But of course then I have to subtract 6 ln 4 here. Right? Okay. So let's rewrite what we have now. I have 3x ln of 4 plus x ln of 11 is equal to 5 ln of 11 minus 6 ln 4. Okay. So a couple of steps left to, and I want to go through a couple of things to make this easier to punch into your calculator as well. But first things first, I can't combine these because they're like terms, but I do want a single x that I can solve for, that I can isolate, right? And that's not too hard. All I have to notice is that the reason that I got all of these x's together, also, by the way, the reason you can combine like terms when you can, because they share that x, I can actually factor it out, right? I can GCF an x. And that gives me two things that I need. One, it gives me a single x. Also, number two, it gives me a multiplication, and all of this is just a number, right? I'm sure it looks, sort of complicated, but it's just a number. And the other side hasn't changed. So if I ever have x times a number, don't I just divide that number over? Sure. So I have x is equal to 5 ln of 11 minus 6 ln of 4, and then divide that by 3 ln 4 plus ln of 11. You can actually, at this point, go ahead and punch that in the calculator, okay? If you punch it in its current form, you're just going to have to make sure and keep up with all of your parentheses. Let me show you a little side trick, though, that you can make it quicker to plug into your calculator. Think back to that last section where we were doing all the log properties. I can actually combine logarithms that are subtracted, and I can combine logarithms that are added. Now, I can't do anything with the division bar, right? That's got to stay. But I can combine the numerator and I can combine the denominator using those rules, right? All I need to do is bring these numbers back in as exponents and then combine them. So then my calculation ends up looking like this. The ln in the top is going to be 11 to the 5th power times, divided, right? Because of the subtraction. Divided by 4 to the 6th. And then over in the bottom here, I'll have an ln of 4 to the 3 power. Oh, well, that one's actually pretty easy, right? That's 64. Plus, so that means times 11. Right? If it helps, instead of writing the 64 there, you can just write 4 to the 3rd. Just some of these other bigger exponents like 11 to the 5th and things like that they're a lot more time consuming, and the whole reason we have a calculator, right? Okay, so whether you plug in this one or this one, I still have a solution for x here. Okay, so let's punch it up and see. I've got ln 11 to the 5th times 4 to the 6th divided by ln of 4 to the third times 11. Okay? So I end up with 3.0971. Okay? Don't forget what this x really stands for, right? It's actually the number that if I were to plug it in up here, right, I would get a 100% true statement. Go ahead and check it when you get a second, right? Take this number that you got, even take a few more decimals, or use the ANS button like the previous answer button. Do 4 to the power of, use some parentheses, 3 times plus 6, and you'll notice you get the same thing when you plug in 11 to the 5 minus that same number. Okay? All right, so the last one over here is find the intersection of these two exponential functions, right? Remember, the intersection is just going to be, of course, where the two graphs meet. And really, it's all I'm going to be doing is setting the y's equal to each other, right? Which means I'm going to be solving this equation. 3 to the 1 minus x is equal to 5 to the x minus 2, which I'm going to work the same way as this one, obviously, right? Real quick, though, let's take a look at about what we should be expecting, right? This is an exponential function with a horizontal reflection, right? So it flips left and right, and it's been shifted 1 to the right. So we're looking at something like this, and he's going to be doing something like this, like that. So there's G. Okay, then H, I just have 5 to the x, and it was just shifted 2 to the right. Okay. So 2 to the right makes my center, somewhere about right there, which means I should have something like this. Whoops. Okay. So what we're looking at is probably something in between 1 and 2 there, unless my graphs are really, really off, right? Okay, so let's find out. I'm going to throw an ln on both sides. I'm going to drop my powers out. I'm going to distribute to get rid of the parentheses. Okay. Then I'm going to add and subtract to get things that are supposed to be together, right? So in other words, I'm going to add this one to this side so that I can have my x's on the same side. And I'm going to add this one to this side so that the things that don't have x can also be together. Okay? So that gives me ln of 3 plus 2 ln of 5 is equal to x ln of 5 plus x ln of 3. From here, I want to get a single x, so I factor out the x. Right? This side's still the same. And then I want to divide both sides by this number here that's times the x, right? This whole number, I'm going to divide it over. Okay? So let's see. Make a little separator here. That means that I have x is equal to ln of 3 plus 2 ln of 5 divided by ln of 5 plus ln of 3. And again, to make this one nicer to plug into the calculator, I'm going to condense it, right? Since these two logarithms are added, I'm going to have a multiplication of 3 times 5 squared, right? Because I have to bring the 2 in as a power. And in the bottom, also in addition, that's just going to be 3 times 5. So actually, we can simplify this even more without much help. 5 squared is 25. Times 3 is just 75. So ln of 75 divided by ln of 15. Right? Okay. So let's see what x actually is. ln 75 divided by ln 15. I get 1.5943. Okay. Now, of course, in an intersection, we want to find the x and the y value. And since they're intersected, right, it doesn't really matter which one, but I have to take this x and plug it into one of the functions to find the y value that goes with it. Okay? And again, they're intersecting, so it doesn't matter which one. Just whichever one is easier for you to plug into the calculator, really. So what's going to end up happening here is I'll just plug it in the top one, right? My y should be approximately, and here's where this is going to come in handy in the calculator. Right now, the last thing that I've calculated was this value. So that's in the current memory as previous answer. So I'm going to use that key and get a lot more accuracy. I'm going to say it's 3 to that power. 3 to the 1 minus, right? This thing's plugging in there. So y is approximately 3 to the power, parentheses, 1 minus previous answer. So I get 0.521. Basically. Which seems about right, even though I didn't put a scale on there, right? Okay. Well, I hope this helps you in your equation solving endeavors. Here's a better look at the intersection of those two functions. You can see the g function is the one in green, the h function is the one in orange. They both share the same horizontal asymptote on the x-axis there, y equals 0. And the center point of g is at 1, 1. The center point of h is at 2, 1, as we were graphing those just using the transformations. And then the intersection right here you can see is I, right? And the coordinates are exactly the same as what we were computing just a moment ago.